Broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome everyone to our three-part webinar series, Rooftop Units Strategies to Reduce Maintenance and Utility Costs. Today you will be viewing part 3 of the series entitled Optimize Your Rooftop Unit. My name is Syed Abbas with Slipstream and I will be moderating today's session. Before we get started, I would like to go over a few items for those viewing online so that you can know how to participate in today's webinar. Each of you should see a control panel somewhere on your screen. The location depends on if you are using a phone or your computer. If you're using your computer, you can expand and collapse the panel by clicking the orange arrow. Also, please be sure to maximize your screen for a better viewing experience. To listen by default, you have joined the presentation using your computer speaker system. If you would prefer to join over the telephone, just select phone call in the audio pane of the control panel, and the dial-in information will be displayed. All attendees have joined the webinar with their audio muted. If you're having any sound or audio issues, head up to the audio tab, click on the sound check. That usually resolves any issue you are having. If that does not work, try to switch in between phone or computer call. If you're still having problems, try closing out to go to webinar and try again. You can still submit your questions to our presenter at any time using the question pane. Simply type your question and submit it. If there are questions we are unable to answer, the presenter will follow up with you after the webinar. For those looking for continuing education, you must watch the entire webinar. In order to receive credit, you will need to take a quiz and pass with an 80% or greater. Please be sure to take some time and fill out evaluation for this webinar, either during or after the presentation. You can copy and paste this link to access the. Next, I would like to thank our sponsor, WPPI Energy, for making today's webinar possible. We are extremely grateful for their generous support of our online education. And now I would like to turn it over to our presenter, Ryan Hogan. Ryan, the floor is yours.
All right, thank you, Syed. Thank you everybody for joining us again. If you are watching the recorded version of this, stop what you're doing, go back and watch part 1 and part 2 first. It's a little bit more logical when you do them in sequence. However, if you are live with us right now and it's your first time joining us, don't worry, we won't lose you. We'll keep things level so you can keep up with us. So we did talk previously in the last 2 sessions about various types of rooftops. We went through all the various components, talked about energy saving things like programmable thermostats, smart thermostats, economizers, demand control, ventilation. We're going to move in further, deeper, and cover a few more of those topics. Then what we're going to do is I have some live equipment behind me here. We'll look at some of that stuff. We can even run it if you guys want, and you guys can openly ask me questions as we're pointing things out physically on equipment. So we did cover, like I mentioned, a few key important energy saving things. Right sizing, as you probably know by now, I'm a believer that almost everything in the entire HVAC world is grossly oversized, not just oversized, but grossly oversized. So getting the right size equipment does save energy. Programmable thermostats, smart stats, economizers, demand ventilation, and then the last one that we're going to focus on right now is staged air volume. So we'll dive into that right now. So staged air volume goes by different nicknames depending on who you're talking to. Single zone VAV, multi-stage air volume, adaptive fan controls, we used to call it back in the 90s. It has become significantly more popular in the past 3 to 5 years, primarily because codes have dictated it in many places. So now it's readily available by manufacturers, hence you can use it anywhere in the country that you want. And at least where we're at here in the Midwest, most states either have this requirement in some situations, or in the case of Illinois, in all situations. And we'll go through what's required by code as well. 2013 is kind of when the tide turned with staged air volume, primarily because of this Department of Energy study that had come out back then. Which seems like, to me, it was like a year ago, it felt like, but now it's 6-7 years the data came out. But it was completely eye-opening for rooftop manufacturers, code people, controls guys, myself. Everyone was like, holy crap, that That's real data. So this study came out, and what they did is decide to test the things I've already told you about, economizers and demand ventilation, and multiple speed fan control, which is not a common thing. A lot of you have had multi-speed furnaces at your house or even variable speed furnaces at your house, but a standard rooftop unit on somebody's commercial building was on and off. That was it, no speed control. So they tested a bunch of live units as well as doing energy modeling on various applications around the country, different types of occupancies, retail, offices, healthcare, different climate zones, different manufacturers. Got a pretty good representation to make sure that the modeling matched up with the live data collected from buildings. The cool thing about this study, assuming you're into studies, is they collected data every single minute, which is a crap load of data over the course of a year. So lots of things to look at. But the really interesting thing for a lot of folks, and what made it hard for people to say, well, that's not a good study, because that's what we do when we see something new that we don't like. We say, that study's bunk. Usually a study takes a control case of buildings. Hey, let's look at these 5 buildings, and we'll compare it to 5 similar buildings and see if the things we improve on buildings B make them more efficient than buildings A. And then everybody always complains, well, yeah, but the people did this, or they changed that, or this got messed up. Or they say, you know what, let's take your building and we'll add these widgets to it and see if it saves energy. And there could be other factors there too. So in this case, all the buildings got retrofitted, and every other day they switched it from controlling it the old way to controlling it the new way. So Monday, we control it the old 1980s way. And then Tuesday, we control it the 2010 way. And then Wednesday, back to the 1980s methods. Every day they switched it. So that kind of eliminated, well, the occupants changed the thermostats. Okay, no big deal. Oh, well, the occupants decided to prop the doors open. Okay, well, that affects everything. So it was pretty cool in that regard, as far as studies go. You probably don't care about that. The real kick out of this was the kind of energy savings that could be had, not upgrading the rooftops, not getting more efficient units, just by doing what we're going to call advanced rooftop controls here. We're saving 25 to 30, a quarter to a third more energy on most of these units. So pretty big savings that were easily had by a couple different things. Almost all of that savings was coming off the fan changes. So yeah, the economizer is cool. We talked about that last month. Yeah, the demand ventilation is cool. We talked about that. But the fan energy savings, that was the moneymaker. To make things a little bit more palatable for end users, they did a comparison in regards to the electric rates that various areas of the country might have and how fast that would affect paybacks. So around here, we're probably around the 10 cents per kilowatt hour for most of our utilities in this area. When you take into account buying the energy, distributing the energy, taxes, fees, and everything, we're in that 10 to 13 cent range. So that probably means we're in that 2.5-ish to 3-year payback range based on the utility rates that we have. All the payback discussions included both the materials and labor. And as you might expect, bigger equipment has a faster payback. All these little control widgets that make this advanced rooftop control and staged air volume happen, they cost basically the same whether I'm putting them on a big rooftop or a little rooftop, but a big rooftop uses more energy. So really fast paybacks on big stuff, slower paybacks on tiny stuff. We looked at 3 manufacturers to see which ones were able to handle this. At the time, which is now 8 years ago, there was only 3 manufacturers of control widgets doing this. Now there's dozens of them, literally. They looked at those 3, they picked one of them, and what they did on these systems is they changed the fan speed to run in 3 different modes, heating mode, cooling mode, and ventilation mode, in addition to doing the economizer and demand ventilation that we had previously talked about. One of the manufacturers also modulates compressor speed. We'll talk about that later on after we talk about the fans today. So what did they do? When they added these controls, which were primarily little tiny VFDs to slow down fan speed, there's other ways to do it. We'll talk about that. But they put these little VFDs on the fans that are existing on existing units. And then when they were in ventilation mode, which means I don't want heat at this moment and I don't want cooling at this moment, I just need my fan to run to bring fresh air in from outside, we ran the fan at 40% of the normal airflow. And then when they were in first stage of heating or cooling, they went to 75% of the airflow. And then when they were in second stage, they went to 90% of the airflow. At no point in time did they go to 100% of the airflow on any of these 66 units that they studied, because every single unit was so grossly oversized, there was not one that needed the full airflow, which tells you something right there. So if we look at the utility rates in conjunction with the size of the unit, and we just take an example. Let's say we have a 10-ton rooftop unit. That's a pretty common, normal, everyday size. So if I get my little laser pointer out here, if I take a 10-ton rooftop, that's these guys down here. If I'm running that unit 14 hours a day and I have a 15-cent electric rate, I don't even need a utility rebate to get this to pay back in 3 years or less. If I have that same unit and I'm running it less hours per day, then I'm probably going to need the utility at that electric rate to pay for half of the difference between my basic unit and my high-end unit, my fan speed controlled unit, in order to get this to pay back in 3 years or less. That 3 years is not a magical number. Some end users want to see 2 years. Some of them are happy with a 5-year payback. 3 is just a really common answer that an end user gives. If you have like a university or something like that, or a school district you're dealing with, they're typically able to tolerate longer payback periods for improvements because they're not going anywhere. They're not going to sell their building next year, usually. Whereas if you got like a restaurant or something, they don't know what's going to happen a year from now. So they want really fast paybacks before they do something. But the bigger the unit, faster the payback. The more the unit runs per day, the faster the payback. And the higher the electric rate, the faster the payback. And then obviously the higher the utility incentive, the faster the payback. So there's a lot of factors involved in determining that. This screenshot right here pretty much tells the whole entire story. So this is a sample of some of those units on the study. The little bar in red shows how many hours per year those units ran in the heating mode. So 5%, 10%, 20% at most. The blue shows how much they ran the compressors for cooling. The green shows how much they ran the economizers. And the purple shows how much they ran the economizers in conjunction with the compressors, or an integrated economizer, as we mentioned before. And that was pretty shocking because that left all this space in the middle with the baby blue, where we were in the occupied mode, people were there, the system was running, but the fan was running, but the heat was not on and the cooling was not on. So you start thinking about all this cool stuff we do to save energy and get better SEER ratings on our cooling systems and better AFUE on our heating systems. It almost kind of doesn't matter because the fan is basically the energy pig. So if we don't find a way to save fan energy, the rest of it is just little tiny baby steps. You can only save so much compressor energy when the compressor is hardly ever on. So we got to pick on the fan. So if you work for a fan manufacturer, I apologize. We're picking on you guys now. Most state-of-the-art line systems from, yes, Ed.
One quick, yeah, there's a question, sorry to interrupt you. Are advanced RTU control standard on new equipment now?
Great question. So are they standard on new equipment? Sometimes. So we'll go through what the code requires here in a minute, but if you are asking the question from Illinois and your unit is more than 5 tons in size, it's required by code and you have to do it. If you're asking the code from Wisconsin or most of the other Midwestern states, we're not quite there. It's code required on zoning systems, but not on regular systems. And the next code cycle, it will be. Illinois is a little faster on the code updates, and I can go into a whole explanation on why that is. But most of the other states are lagging by a couple of years. So yes, in Illinois, it should be standard for bigger units and even mid-size units. No, not standard in other places. With that being said, you can buy a unit in Illinois that's not code compliant. I mean, the company I work for during the day, we sell non-code compliant units to people all the time. We offer the code compliant, we suggest it, we give them energy calcs, we show them why they should do it. And then somebody says, yeah, I don't want to deal with that. And then they buy the other unit anyway. It's crazy. But we only sell to contractors, so we're not complying with code. We don't have to comply with code. The person pulling the permit and installing the equipment would have to comply with code. So it's a whole weird loophole thing. So if you are in Illinois and you want to save this energy, you need to tell that your contractor you want to do this, because they may or may not decide to follow code, or they may not even know what the code is. So you're gonna have to ask for it. Just like anything else, you're gonna have to demand the things you want to make sure that you get them. If you don't ask for it, you probably won't get stuff. Most of these units will only have 2 fan speeds, even though that Department of Energy study had used 3 in their study. Most units can only handle 2, and I'll explain that when we get to the tie into the economizers. And then from a code requirement, most of them only have 2. And this is what the requirement typically is. When you're on first stage of cooling or in the fan only mode, you run at 2/3 of the speed. When you're in second stage of cooling or any stages of heat, we run at maximum speed. So that basically means when we're in this red bar down here, we're in maximum speed. and let's just say for argument's sake, half of the dark blue bar, we're at maximum speed. Everything else is at the lower speed. We typically use VFDs to do that. VFD, actually, it's almost the same one that's in the picture, coincidentally. VFDs have gotten much, much smaller over time. They used to be literally as big as me. Now this guy is probably the biggest one I'd ever seen in any rooftop unit. Most of them are smaller like this. And even now, some of the ones that we're using are like half of this size. They're getting smaller and smaller, which means even on a little 3-ton unit, we can fit a VFD in there, and space to install it shouldn't be anybody's objection. Now, the reason we use a VFD instead of a 2-speed motor, because a 2-speed motor is a thing. 2-speed motors are not inexpensive. You basically have doubled electrical windings. They are pretty costly, and the cost of VFDs has gone down over the decades to the point where it's less expensive to buy a regular motor and a VFD than it is to buy a 2-speed motor. So we just use the VFD. The other nice thing is in the VFD, someone could change the airflow settings. If they decide 67% isn't right for them and they want to do 61%, they could do that. Whereas a 2-speed motor, you'd be kind of locked in and you'd have no choices to balance that airflow if you wanted to in the field. So if you're not familiar with VFDs, and some of you probably are because Slipstream and Focus on Energy and everybody else has done a lot of education on that. So we only got one slide on VFDs today just to catch everybody up who's not heard of them. You can get these in new pieces of equipment. You can retrofit it to existing. It's very common for VFDs to be on fans and pumps, but you'll also see them on compressors and escalators and all kinds of other stuff as well. So what a VFD does, variable frequency drive, is it changes the frequency of the signal that's going to the motor. So it basically varies the input of power to the motor. So you don't get full power, you're only going to get 80% of power. You're going to get 72% of power. You get 31% of power. So it modulates that power going into the motor to save energy. Because you don't need the full airflow all the time. There's times you need it, right? When it's 92 degrees outside and all the stages of cooling are on, okay, I need full airflow. But all the rest of the times of the year, we don't need full airflow. Fan systems in general are oversized by 60% in this country, which is astonishing. I have seen plenty that are double the size they're supposed to be. I've never seen one that wasn't at least a little bit oversized. So kind of our discussion like we had with cooling sizing, fans are in the same boat. They're all oversized and many are grossly oversized. I know at a lot of places, a lot of manufacturers of rooftops will sell a low static fan, a medium static, and a high static. Almost every distributor I know always stocks the medium static fan because then they figure, well, I'm right, like, most of the time, right? It's kind of in the middle. If I pick the low one, then I can't help somebody who needs high static. So a lot of these buildings get this medium static fan, even though the vast majority only need the low one. But that's what they do just to kind of minimize their stock. So if I took a pretty large motor and it cost me $1,000 a month to run that motor, so this is a big rooftop in this example, and it was running at full speed and it cost me $1,000 a month. If I slowed it down to 75%, what would you think it would cost? The vast majority of people would say $750. It's actually $420. If I cut the speed in half, what would it save? Well, at this point, you wouldn't be guessing 500 because you know it's going to be less than 420. $125. So if I cut all your fan speeds in half, I would cut all of your energy usage by an eighth, or almost an eighth. It's a pretty, actually it is an eighth. It's a pretty substantial amount. This is due to something called the fan laws or the pump laws. Or if you work on fans and pumps both, then you play nice and you play Switzerland and you call it the affinity laws, which also sounds cool because it's a superhero kind of thing, right? The other nice thing about these VFDs, other than the energy savings, is the fact that when you first turn them on, they don't apply all the power immediately. A normal unit would do that. It would apply all the power immediately. It would have a lot of stress on the belts and the motor, and you would hear the loud booming noise and the ductwork expanding and all that stuff. That's not how a VFD works. A VFD goes up slowly. So it's more like when you're driving your car and you slowly put the gas pedal down as you accelerate from stoplight to stoplight, or at least that's how I drive now, right? When I was 17, that's not how I drove, right? I would just gun it. At the next stop sign, I'd slam on the brakes, gun it, slam on the brakes, right? That's a normal unit. That's a normal rooftop unit's fan today. But if you put a VFD on there, you're driving more like me, a 44-year-old who drives a Prius and tries to optimize his miles per gallon. I'm like coasting to the stop signs, right? So that's what this is going to do for you. It's going to have less wear and tear on your vehicle. The car I have currently, it's 7 years old and I have 130 some thousand miles. I didn't get new brakes or tires until 120 something. I went 120,000 miles on my original brakes and tires, right? When I was 17, every 12,000 miles I had to get new tires. It was crazy, right? Just the way you drive. And this is going to help you drive your HVAC system like an old person. Paybacks on VFDs are usually pretty quick. Once again, the bigger the system, the faster the payback. The smaller the system, the slower the payback. So we had a little poll question we wanted to ask you guys, just to see. I'm going to launch that now. If you see a VFD reading 100% speed all the time, when you walk in the mechanical room or into a rooftop, on a pump or a fan, and you see that VFD on there, and on the screen it says 100%, what do you think that means? You think it's operating normally? You think that means it's an extreme weather day? Do you think it's improperly set up? Or do you think something's broken on the display and it's not really at 100%? I'm just curious to see what you guys all think that means. If you guys have questions for me, feel free to type them in, and Syed will be monitoring those, and he'll rudely interrupt me and tell me to shush while he reads me the questions. No, I'm just kidding. He's not rude ever. All right, 56% of you guys answered. If anybody else wants to answer, this would be your time. All right, so I'm going to close this. I'll share the results with you. So most of you got it right. Usually it means that something's not properly set up. I did building automation systems for like 10 years in the 90s and early 2000s. And anytime I walked into a mechanical room and saw the VFD at 100%, first thing out of my mouth was, that's not right. And I'd be like, what do you mean it's not right? It's always at that. I'm like, yeah, that's my point. It could be an extreme weather day, but that means your unit's not oversized and your fan's not oversized, which that almost never happens. So if it's at 100%, it's probably not right. Now, if it's at 100% for a little while, okay, maybe it was that freaky 97-degree day, or maybe it was in setback mode, saving energy, and it first powered up in the morning and it's got a lot of catching up to do. Okay, maybe. But if you see it at 100% all the time, it's definitely not set up correctly. Or it could mean that someone, the operator, bypassed it. I've had that a lot of times too. People are like, I don't understand what that thing does. I don't know what it means. So I went over there and I turned that switch that instead of auto, I put it in manual on. And now it just runs for me. It's perfect. I'm like, yeah, it's perfect, but it saves no energy and it's loud as heck. So it's probably improperly set up if you see it at 100%. I'm going to spare you guys the math lesson because that would be boring, even though I love me some math. But what you need to know is that the horsepower, which is an indicator of the electrical power that I have to buy from the utility to run my fan or pump, the horsepower varies as the speed varies, but it's to a cubic function. So what that means is if I cut my airflow, let's just say in half, right? This orange line is my airflow. If I cut my airflow in half, look what happens to my power, right? It goes from 8 down to 1 unit of power. I cut my airflow in half, I cut my power by 7/8. So it's not a straight line relationship between those two things. So if I take the math and I just solve it out in this particular case, if I slow my fan down to 67%, which is what many codes require me to do with 2-speed fans, if I do that at 67%, my brake horsepower actually reduces by 69%. So I cut my speed back by 1/3, but I cut my energy by 69%. It's pretty substantial. And if you can get a lot of run hours there, and like we said before, those baby blue bars, it's a lot of run hours that I don't need full airflow. I can save a lot of energy in a building. This is kind of duplicated what I already showed you, just a little different way to look at it. When I have a 2-speed fan system on my rooftop, vent only, which is the vast majority of the runtime, fan only during occupied hours, or first stage of cooling, we throttle it back. The reason we do it on first stage of cooling is because that really helps us with dehumidification. Lower airflow helps us dehumidify. And if I can dehumidify the space better, you'll be more comfortable at a higher temperature. So instead of the space needing to be, say, 72 degrees for you to be comfortable, if I dehumidify it better, maybe it could be 74 and you're equally comfortable because the humidity is lower, and that will help me save energy as well. Full cooling, I need the full airflow because that's what I designed it for, right? And then heating, I would love to have 2 heating speeds, one for second stage heat and one for first stage heat. It's just that I can't go down to the 67% for first stage heat because it's not enough airflow for most of the heaters. So I'd have to be somewhere in the 70 or 80% range. And the reason I can't have 2 fan speeds or 3 fan speeds, excuse me, is because the economizer can't handle it. And I'll show you that in a minute. So if you're in Wisconsin,
We have one more question on the fan speed. So the question is, do you need a special thermostat to control the fan speed?
Excellent question. If you're just going to do one of these 2-speed fans, you do not need a special thermostat. A regular, everyday, 2-stage heating and cooling thermostat would be able to handle this. I'll show you in a little bit how we wire it to make that happen. Yeah, but you would not need anything special. Your favorite thermostat, as long as it's, you know, a code compliant 2-stage thermostat, would be able to do this.
And then there's another comment in the question is, it could be all actually undersized possible. Just a comment.
Say that again. Is it?
It could be all actually undersized possible. I think so. He might.
Is undersized.
Yeah.
It's possible. In 23 years, I've never seen an undersized fan system yet, but yeah, of course it's possible. Usually what happens if something's undersized for heating, cooling, or airflow, people complain, and then whoever installed it and designed it goes in and fixes that problem and puts something bigger in. But when it's oversized, people don't necessarily know that. They don't know they're wasting energy. They don't know that's the reason their humidity is not right. So they don't really complain about it being oversized as soon as they would about it being undersized. So undersized is something extremely rare in our industry. If you're in the state of Wisconsin, which 2/3 of you guys are, there are times that the fan speed control we're talking about here is actually required by code. Specifically, if you have hydronics on your system, meaning I have hot water heat as opposed to electric heat, heat pump, or gas heat. If you have hydronic heat, or if you have multiple zones, meaning you have zone dampers in the duct that open and close, like VAV, VVT, constant volume zoning, something like that. So if you have those kind of buildings, those kind of systems, then that's when the fan speed rules will kick in. And specifically, the rule is if you are above 65,000 BTUs, which would be more than 5 tons of cooling, then you're going to have to do a 2-speed fan. For those of you guys that are in Illinois, this rule has since changed, and the more modern version of the international code, so the 2018 version of the code instead of the 2015 like we have in Wisconsin. If you're in Illinois, then the rule for it being tied to hydronics or multiple zone goes away, and then it's all systems bigger than 5 tons have to have 2-speed fans in them. So it's a big difference there. So I showed you guys this software a couple weeks ago when we had the other webinar. It's same software, same exact example. It's still Madison, Wisconsin. It's still an office building. It's still a 10-ton unit. In this case, I have a Wisconsin code-compliant model of rooftop unit, and it has an economizer in it. And I have the exact same model of unit, nothing different whatsoever. Same cooling, same heating, same compressor, same coils, same everything, same motor. And the only thing we've done is we added a 2-speed VFD onto that motor. Right? If you remember, we were looking at before at economizers and DCV. In this particular example of this size unit, they were saving like 6-7% of the energy. So when I go ahead and click the next slide, you'll see how much energy it saves just by going to this 2-speed fan. Except for my slide won't kick. Right? 29%, $700 on this little unit. So yeah, before, put the economizer in, great, save 6%. Put the DCV in, save another 6-7%, great. In this case, put a VFD in, save 29%. It's absolutely massive, and it's so easy to do. It's become one of the most popular retrofit items in the Midwest lately. By the way, the same tool gives you kind of a breakdown showing where the savings is coming from. You can see the vast majority of the savings, $755, is coming by this fan speed control, slowing it down to 67% most of the run hours of the day. There's a slight savings on the cooling side because the cooling energy includes fan energy in its calculations, the way we model cooling, SEER and IER. There's a penalty on the heating side. I'm gonna buy more gas actually. And that's kind of weird. At first when we started doing these calcs, we're like, why is this happening? Motors, if you didn't know, have a little bit of waste heat associated with them, and that waste heat goes into the airstream. So when I slow the motor down, it has less waste heat, which means I need a little bit more real heat from the gas side to make that up. but I'll happily buy $71 of gas to save $750 of electricity. That's an easy no-brainer trade for me. For those of you in Wisconsin, which is most of you, the Focus on Energy program has something called Advanced Rooftop Controllers. They will pay you a rebate of $90 per ton if you retrofit your existing rooftop units with the things that we've been talking about: economizer, demand control ventilation, multi-speed fan control. So if you add those three things, two things we talked about last week, and now the fan speed control we're talking about today, it's $90 per ton. So if you have a 10-ton unit, it's $900. Yes, I picked the 10-ton unit because they made the math easy for today, and I'm lazy.
Right.
Yes.
Sorry to interrupt you. There's another question. I think so it's related to last slide. Would the two-speed strategy for two-speed strategy? I think so. They are talking about might be for the fan.
With the two-speed strategy, what would it?
For would the two-speed strategy for? I'm not exactly sure what James Clark is saying, but
This question here, I look like he stopped typing. It's like he would the two-speed strategy for, and then blink. It seems like there should be another part of that.
Mm-hmm.
So James, if you want to clarify that, we'll circle back to you.
Perfect. Thanks.
All right, so I mentioned that you can do this with a regular thermostat. Yes, you can get a building automation system and DDC controls, and you can do it, and that's totally fine. Or you can get one of those kits like they did for the Department of Energy, but you can also do this with a regular thermostat. Here's the regular thermostat. Here's a regular circuit board in the unit. Here's the regular motor in the unit. Usually we'll recommend an inverter duty rated motor. In some cases, you can retrofit a VFD onto an existing motor. Inverter duty rated means it's basically built to handle the VFD, which means it has more insulation in the windings. So as the VFD slows down and you get less air across the motor to cool the motor, you don't have any chance of it overheating. But a lot of VFDs are retrofitted on standard motors as well. So the VFD manufacturer can help you make that decision. So I got the stat, I got the board, I got the fan, the motor. I already would have had those three things. The two new things that I'm going to add are the variable frequency drive. That guy's going to slow my fan speed for me. And then I'm going to add 4 relays into here. In this case, it's a relay board that has 4 relays in it. You could also have 4 individual relays if you want. And the job of those relays is going to be to intercept the signals that the thermostat is sending anyway, right? He's already sending a call for heat, a call for fan, a call for first stage cooling, and a call for second stage cooling. I'm going to intercept those, let them do the normal thing and turn the compressors and gas valves on. But I'm also going to intercept those and run them into this VFD. And then the VFD is going to be programmed to know, oh, if this relay kicks on, that means go to fan speed 1. If this one kicks on, fan speed 2, this one fan speed 2, this one fan speed 1, right? So a VFD, 4 relays, and a little extra wiring gets the job done. Now you're also going to have an economizer controller that can handle that. Because the economizer, not every economizer controller has the ability to have 2 damper positions. So some of them, like this Honeywell Jade controller I'm showing here, can do it. The Belimo Zip controller can do it. I'm sure there's others as well. I'm gonna need one that can have 2 minimum damper positions. Because if you think about it, when I slow my fan speed down, I'm gonna be providing you less ventilation air. Well, the code doesn't let me do that. I still gotta provide you the same ventilation air. So when I slow the variable speed fan down, I actually have to increase the ventilation damper position. And when I speed the fan back up, I can throttle the damper position back. So I'm always sucking the same amount of fresh air in, regardless of how fast the fan is running. So you do need to have an economizer controller that can handle that. So you're going to get a VFD, you're going to get 4 relays, and you're going to get a different economizer controller than you planned on getting otherwise. Now you may be getting this controller anyway because it's required in a lot of code requirements either way, like we talked about previously with the fault detection and diagnostics. So you're probably already buying this economizer controller. So really you're just getting the fan VFD and the fan relays. This kind of illustrates what I'm talking about with the ventilation rate. So right now my fan's running at maximum airflow. This blue line here is showing the airflow going into the space. The yellow line is showing the return air coming back. My return air goes through, it gets heated, cooled, filtered through the blower back into your space, and that's what's normally happening. And I got some portion of ventilation air coming in to go along with that. Right, so in this example, let's say that's 800 CFM, 800 cubic feet per minute of ventilation air, right? When I slow the blower down to 67%, but I don't move these dampers, now instead of 800, I only have 500 CFM of fresh air coming in. That's not going to be compliant with code nor desirable. So I have to move these dampers to a little bit more of an open position in order to get my 800 CFM. So fan speed goes down, dampers open up a little bit, fan speed goes back up, dampers throttle back down. So always get my 800 CFM in this example. There's several manufacturers that will sell you a new rooftop unit that already has all of this built in. You don't need to do anything special. You just order it that way and it's done. Or if you have an existing unit and you want to retrofit it, there's those 3 manufacturers that have the kits that the DOE had called out their names of. And then I've also been building for the past 5-6 years my own kits with Honeywell stuff. And you could probably do it with anybody's stuff if you want.
So
actually start doing LSI stuff. Yes.
Yeah. We got the question from, sorry to interrupt you, from James. Yeah. He's saying, would the 2-speed strategy for RTU work for a constant volume hospital AHU serving multiple zones, especially considering the fan is probably oversized?
Yes, you could do that. You could add this to a rooftop or air handler that serving multiple zones. The only thing that I would caution you on are if the zones have dampers, so it's a VAV system, then you should switch from constant volume to full-on variable air volume. Staged air volume is kind of a hybrid between variable air volume and constant volume. So if you have zone dampers, VAV's dampers specifically, I would go directly to a VAV control. And it's even easier to do that than staged air volume. You buy the same VFD you would buy for staged air volume, and you wire a pressure sensor to it instead of wiring relays to it. It's very easy to do. I've been retrofitting stuff like that for 30-some years. If your hospital has constant volume air handlers with reheat coils and no zone dampers, that's when you're going to have to be a little bit more cautious. If it's a hydronic reheat coil, not the end of the world. If it's electric reheat coils and you provide less airflow, you're going to trip out those heaters. So those ones you'd have to pay attention to, and you might not be able to do it, or maybe you can't do it as much. Maybe just slow it down from 100% airflow down to 82%. That's all you can do and still have enough airflow for those heaters.
Thanks, Ryan. While you're on a question, there's another question. If it saves so much energy, why does the energy code only require the 2-speed fan for zone system instead of all systems?
Yeah. So here's what happened. I'm going to go back to the code slide because I know nobody loves code slides. Here's what happened. This code book, IECC, International Energy Conservation Code 2015, is actually a misprint. And if you talk to the guys at the International Code Council, they will tell you this. This section here, fan control and fan control airflow below it, 403.4.1, was supposed to be its own section. But instead, it accidentally got inserted underneath this heading for hydronic and multiple zone. So legally, it only applies to hydronic and multiple zone, and hence people didn't have to do it. When they first launched the new code and they were doing training on it, they kept saying you got to put it on every system, and we were like, why? It only says hydronic and multi-zone. Like, really? Why is it only? Oh crap! They literally put it in the wrong spot. It should be basically 403.5 instead of 4.1. The 2018 version of the code, the book comes out every 3 years. That corrects it. So for Illinois, which is on the 2018 code, it's corrected. For Wisconsin, it's not corrected yet. So once we change over here in Wisconsin, it will eventually come. So it's a misprint. On the plus side, because it's not code required, that allows utilities to pay incentives to do it on both existing and new systems. Normally when something's code required, a utility can't pay you a rebate for it because they can't pay you to do the bare legal minimum. At least they shouldn't pay you to do the bare legal minimum. So there's a little benefit there. You can get rebates on it in Wisconsin for a little while longer to help pay it down. This is just if you're interested. This is the off-the-shelf Honeywell kit. This is stuff that I got tired of buying kits for projects, and I was like, we have all this stuff already in inventory. I can just make my own kit. And honestly, most of this stuff's already on the unit. So everything on this list, except for the part where it says down here, the last two things, VFD and the relays, other than that, all the other stuff was already buying on a regular rooftop job anyway, because that's all the stuff you need to make the economizer work and the regular thermostat and all that. So I was already buying all that stuff. So I was like, if I just add a VFD and 4 relays, I'm done. And then send people out a wiring diagram. In this case, the Honeywell wiring diagram already has it built into their manuals and shows you how to do it. All this stuff, it looks pretty scary, right? It's a lot of stuff there. All that stuff you're already wiring on a normal economizer job. So you're already doing all that stuff. The only thing that's extra is these 4 relays down here for W1 heat, Y2 cooling, Y1 first stage cooling, and the fan command. So he's just going to intercept those commands and let them go over to the VFD so the VFD knows what to do. So it's really quite simple to set this up. I mean, quite simple for an HVAC tech or an electrician, right? My grandma's not going to do it, but for people that are in this industry, it'll be easy. If you are in Wisconsin, they do call out by name the manufacturers that have approved controllers for that advanced rooftop control rebate. And that list only used to have 3 or 4 on there. Now there's a whole bunch of them on there. And if you have another one that you think should qualify, send it to them. They'll review it and see if it meets the requirements. But if you look at this covers like 90% of what you'd see on any project. But there's probably some other little niche ones out there that people don't know about. So if you stick with these, you'll be in good shape. All right, let's launch that second poll question because the poll questions are fun, at least fun for me. Which typically saves the most energy? High efficiency cooling systems, high efficiency gas heating systems, multiple speed fans, or programmable thermostats? While we're taking a look at that, if anybody has other questions they want to send in, please do so. I'd be happy to answer stuff. I'm gonna go turn my lights on. So I'm gonna go look at the inside of the rooftop and see stuff better. All right, 46% of you answered. Anybody else wants to answer, please do so. All right, I'm gonna close this poll in 5 seconds. So pick something. All right, 81% of you got the correct answer, as I would expect, because we're literally just talking about that. If you wanted a number 2 answer, you guys are correct on there. The second most likely thing to save energy would be a programmable stat. And there are certain job sites that the programmable stat might save more than the multi-speed fan, especially job sites that were previously running 24/7, but they're only truly occupied like 8 or 10 hours a day. Those ones, the programmable stat might beat out the fan speed control. But for a normal building where you're running it, 10, 12, 14 hours a day, the fan speed control is going to win. The third would be the high efficiency cooling. And the last, sadly, would be high efficiency heating, only because on a rooftop unit, low efficiency heating means 80%, high efficiency means 82%. That's it. There's nothing really more efficient. So there's not a lot of room to work with there. But if you could get something higher efficiency, then maybe heating would get really exciting. But it's really hard to get high efficiency heating in an outdoor mounted unit. I'm going to briefly talk about compressor control, just because this does tie into some of the stuff we were talking about with stage 1 and stage 2 of cooling in relation to the fan. The way I like in compressor control is if I got a big dinner going, right, and I'm cooking all kinds of pasta and sauce and everything, I'm probably going to use all the burners on my stove, right? But if I'm just cooking something for myself and I'm all alone tonight, why do I need all the burners on? I don't need them on. You would never put that pot on there and light all 4 of those burners, or however many burners are in that picture. You wouldn't do it. There'd be no reason to. You'd only like the one you would use. The same thing's going to happen with compressor control. If I have 2 compressors, I'm just going to use one. If I have 8 compressors, I'll use 1 or 2 whenever I can, and only use all 8 of them on days that I absolutely have to. So that's the idea behind this. And if I can use one instead of lots at most of the hours of the year, it's going to save me some energy. So what ways can I control compressors? First thing is we got to recognize that we don't need all the capacity all the time. We talked about this on the first webinar. There's very few hours that you need all the stages, right? So for Southern Wisconsin, our design days are like 87, 88, 89 degrees, right? Somewhere where my red dot is here. There's very few hours of the year on a rolling 30-year basis that I'm actually above 90 degrees. It's really small. So I don't really want to design my system for that. I want to design for the 87, 89 degree day. And you can see from an energy standpoint, if I can do an awesome job of saving energy in here for cooling, I don't really care if I waste energy on some freaky 90 degree day, because I want to save it all these hours of the day. So ways I can control it. I can have just one compressor and it turns on and off. That's what you have at your building now, very likely. Most of you have a single stage unit, it turns on and off. At your house, you have a single stage unit, it turns on and off. Most of you. It's pretty boring. It's not very comfortable. It does a crappy job of dehumidifying, but that's what you have. If you can get 2 or 3 compressors instead, then I can stage them upward and only use the capacity that I need. That's going to save me energy. It's going to keep my humidity under control. because instead of banging one on and then banging it off and banging it on and banging it off, I can run a small one for a long period of time and it'll constantly pull out humidity for me. It's very difficult to retrofit. It's not impossible, but you pretty much have to be a refrigeration engineer to figure out how to retrofit into an existing unit. So you're pretty much going to make this choice when you put a new unit in. The economizer, DCV, fan speed control, all that is easy to retrofit. Thermostats, but this is not easy to retrofit. It's probably going to only happen when you're going to throw your old unit away and you're going to buy a new unit. So most of you have a single compressor in unit, looks like that. You might have two compressors in there. That's a big difference, and it's going to save you quite a bit of comfort problems if you can get that second compressor. Or you might have one compressor like this unit, and the unit behind me over here, which one compressor and it runs at 2 speeds. That's nice because then I only have one thing piped in, makes things a little bit easier in that regard, and it's a little bit less expensive. Most 2-stage residential units are like this. They'll have a 2-stage compressor. Small commercial units, typically 3, 4, 5, 6 tons, use residential compressors, so they're typically like this as well. Then when you get to the big units, 15, 20, 30, 50 tons, they'll typically have 2, 3, 4 compressors available for them instead of multi-speed compressors. Another thing we do is we might take 2 compressors and get you 3 stages out of it. These are just on-off compressors. They're just 1 stage each. But instead of making them the same size, let's say you had a 10-ton unit, instead of buying 2 5-ton compressors, maybe I'm going to buy a 4-ton and a 6-ton. And I can run compressor 1 to get 4 tons of cooling, or I can shut that off and run number 2 to get 6 tons of cooling, or I can run both of them at the same time to get 10 tons of cooling. So that's kind of a unique way to get more stages of control. More is better in this case, without having to have more cost. I'm going to skip this. If you have old compressors like this, reciprocating compressors, the only thing I want you to know is that you can add unloaders to them easily as a retrofit to give them more stages. Just know there's 2 kinds of unloaders, pressure unloaders and electric unloaders. Pressure unloaders are for constant volume equipment. Electric unloaders are for variable air volume equipment, and you can never use the opposite the other way. If you have any questions on that, ask me. These are becoming more and more rare, so I'm not going to spend more time on it today. You can also get a compressor that can unload itself, a digital scroll compressor. Scroll compressors are what most of you have in your units, but you can get one that unloads itself internally. And we don't have time to dive into that today either. Just know that it can run at less and less capacity. And most of these modulate from 10 to 100%. So just pretend for right now, each percent is a stage. You got 90 stages of capacity essentially, instead of 1 or 2. So you got really good control in this case, and a lot of energy savings can be had. You can also get, what's more common nowadays is to get inverter-driven compressors. You don't see a lot of this on commercial yet. It's become very popular residentially in the past 6 to 8 years. But basically, you're going to get a little VFD like this for your compressor. It's not going to look like this. It's going to look like the one I have in the bottom left picture. But you'll be able to slow your compressor down that way. And that's becoming more common. Most manufacturers won't let you retrofit it yet, but they will do it on a new system for you. If you're going to have a zoning system like I mentioned before, then we're going to have additional code rules that kick in for all the Midwestern states, basically. Michigan, Wisconsin, Illinois all have these same rules. If you have zoning systems with dampers, then you're going to probably require 3 stages of cooling instead of 2, or 4 stages of cooling, depending on how big your unit is. We have a thing called hot gas bypass. Do not let your contractor talk you into this as being one of your stages. For one, the code doesn't recognize it as a stage. For 2, it's an energy waster. What it basically does, without explaining the whole refrigeration cycle, your compressor is supposed to send the hot refrigerant to the condenser outside to throw that heat away, and it does that, but it also takes some of that hot refrigerant and shoves it back into your evaporator coil, which is the indoor side of the system, and it falsely overheats the evaporator coil, which makes the compressor run longer to meet your set point, and hence you get good dehumidification control, but you do it by running your system balls out and overheating things that shouldn't be overheated. It's a Band-Aid. It's not a good idea. Sometimes you got to do it, and you can retrofit this quite easily, and there's even a manufacturer, RAL, that makes a retrofit kit to do it that does it a little bit energy savings compared to regular hot gas bypass. But whether you do regular hot gas bypass or a RAL device, it's still going to use way more energy than if you did nothing. So you're going to do it when you have to because someone oversized the system and this is your Band-Aid, but you should not do it because you think it's going to save energy, even though the raw literature will talk about it saving energy. Just saving energy compared to what is always the question. And I'm not sour on the Rawl guys. We use their stuff all the time. It's just, you got to use it in the right spot. Additionally, the code does not require you to use hot gas bypass as one of your stages. You still have to have your 2, 3, or 4 stages, not counting hot gas bypass as one of them. Another way to get good dehumidification, other than slowing the fan down and other than adding more stages, would be to have some kind of dedicated dehumidification coils. So we can do that. So hot gas bypass is one way to get things done. Staging gets it done. But there's a thing called humidizer, which some manufacturers use, or hot gas reheat. So don't confuse hot gas bypass with hot gas reheat. Hot gas reheat and humidizer are ways to take, well, I'll show you the drawing. It'll be a little bit easier. Humidizer is a 3-stage version of hot gas reheat. It's just like a little beefed up version. But basically what it does is it allows you to run in a cooling mode, or it allows you to run in a dehumidification mode, which we call hot gas reheat. So a humidity sensor would be in the space and it would engage the system. And we can also run in a mode that combines both temperature and humidity control simultaneously. I wish we had time to dive into all the piping diagrams of that. I have them on here, but I'm looking at my watch thinking it might, maybe I'll just do like the 30-second version of it. When you have humidizer, you get an extra coil in your unit. So you have a condenser coil and an evaporator always on all systems, and they give you a third coil that sits downstream of the evaporator coil for your air that will blow into the duct and into your space. And then in normal temperature control mode, the compressor rejects heat outside to the condenser. It goes through TXV into your evaporator where the cold refrigerant has air blowing across it, brings the cold air into your space, and that cycle continues on. If you need help with the refrigeration cycle, let me know. I got videos on that to help you guys out as well. When I go into one of these dehumidification type modes, we have 2 of them in here, right? We have the one that's dehumidification only, which is this one here. So in that case, I open up a valve that allows some of that compressed refrigerant to bypass the condenser and not reject the heat outside, and instead runs it over to this extra coil that we put in. So then I have air blowing across my cold evaporator, bringing it down to its dew point, pulling moisture out of it, cooling the air off. But because I don't want to cool the space, because I'm in a dehum only mode, it goes through this humidizer coil and gets tempered back up. So instead of me blowing 55-degree air out of the register, I blow 70, but it's already been dehumidified. The last option would be I need temperature and humidity. So I don't bypass the condenser, I reject the heat outside, but then I use the humidizer coil basically as a second coil to get me more surface area so I can do even more work with it. So it's a pretty cool system. Check it out if you have applications like fitness centers and stuff like that that need more than regular dehumidification. All right, the other thing we want to talk about that was requested that we add into the discussion was pairing up boilers with the rooftop units. This is something that does happen, I'm gonna say reasonably often in Wisconsin. It's not like it's an everyday thing, but maybe like, I don't know, 10% of the buildings might do something like this. A little bit less if you're in Illinois, but Wisconsin does it a little bit more, probably because they have more heating hours than we have in Illinois or in Indiana. But what you can do, there's different ways you can do this, but instead of buying a rooftop with a gas heater, I may buy a rooftop that has no heat in it at all, and then in the duct, I'll put a hydronic coil, a water coil, and I will pump hot water from my boiler into that coil as my rooftop blows air across it. Why would you do that? That's more work. Well, the reason I'm going to do that is because a rooftop unit, the best ones are 82% efficient. Now, there's a couple custom special ones out there where you can get up into the 90s, but that's super niche and it has its own set of problems. Normally, to get above like 86% efficiency, it means I have to have a condensing type heating system, which means water, condensate water, is me draining out of it, out of my furnace, out of my condensing furnace, out of my condensing boiler, something like that. Well, on a rooftop unit, if I put a condensing heater in there and that condensate had to drain away, in the Midwest, where would it go? It would try to dump on the roof because it's below freezing, the pipe's gonna freeze and I'm gonna have an ice block and the whole thing's gonna back up and it's gonna be a problem. So instead we have an indoor boiler that's condensing, and those will be typically 94, 95, sometimes even 97% efficient. And that guy can be crazy efficient, and then we'll just send hot water over to the duct system. So we can have that boiler feeding duct coils. We could also have it feeding radiators in the building. That's fine too. Baseboards, radiant floor systems, right? We can do any of those kind of things with a boiler. There's lots of flexibility there, and we can talk about boilers for 8 hours. And I'd love to do that with you guys. It's another fun topic. If you're going to combine the rooftop with the boiler, make sure that your heating zones line up with your cooling zones. It's horrible when somebody puts in radiators and this one rooftop overlaps into two different zones of radiators, or worse, there's one radiator that happens to be served by two different rooftop units. It's a mismatch. It's confusing for the occupants. Line the cooling zones up, rooftop, with the heating zones up, radiator, boiler, heating floor, etc. So make sure they match up. Now you may have more than one thermostat in there, that's fine, or more than one radiator in there, but I'd like to have one single thermostat turn my cooling on and open the valves to both of my radiators, or all 10 of my radiators, or however many I have in this case. One thermostat controlling both. If you have two thermostats, the problem ends up happening that, well, if somebody makes this one call for cooling and makes the other stat call for heating, now I have heating and cooling running at the same time, which is a massive energy waster. So one thermostat controlling both is the way to go. There's some unique wiring. If you want to do that, let us know. We can help you out with that, but make sure it pairs up kind of that way. You can have more than one boiler as well. I can have one boiler feeding each system. I can have two boilers feeding one hydronic loop, and that loop feeds 10 different systems. There's lots of flexibility there. We can move things around. We do that a lot. We'll put modular boilers in and have a bank of, in this case, what is it, 8 on the left, or this other plant has 5 boilers on it. 5 boilers may be serving 72 radiators that are also served by 6 rooftop units or something like that. 6 rooftops, 6 thermostats. The radiators that are in that area for rooftop 1 go with the thermostat for rooftop 1. Pair them up evenly. Condensing boilers, you have to have low temperatures to get them to condense. This is a typical drawing or typical chart out of the ASHRAE handbook. This is showing you the water coming back to the boiler. If I have cooler water coming back to the boiler, which means I have cooler water leaving the boiler, I move backwards on this scale until I get to this point here. When I get about 130-degree return water from the boiler or so, or less than that, it goes into a condensing mode, which means I get freakishly high efficiencies. So I might have a boiler that's rated for 86% efficient, but if I give it 100-degree water, now it's behaving like a 92% boiler. So I want that colder return water. So what that means is you shouldn't set all your boilers for 180 degrees, especially if you have a condensing boiler. If you have a condensing boiler, try to figure out the lowest water temperature you can operate it at on your -5-degree day or whatever you need, and see which ones still say. If you can get it done with 171-degree water instead of 180, that'll save you some energy. If you can get it done with 110-degree water, it'll save you a lot of energy. We can also put it on the outside air reset curve. So what that means is if you really do need 180-degree water on the coldest day of the year, that's fine, we'll give you that. But we'll put a controller in that babysits the outdoor air temperature, and as the outdoor air temperature warms up, we give you cooler and cooler water. So I can spend most of the year in a condensing mode and only the really, really coldest days of the year in a non-condensing mode. All right, let's wrap all that up and then we'll do any kind of Q&A you guys want with the rooftop units. So we had talked a lot about various rebates. There's a bunch from Focus on Energy. If you are a WPPI customer of a specific utility, they may have some rebates that are in addition to the Focus rebates. Sometimes that happens, not always, but sometimes it does. But you all should be eligible at least for the Focus rebates, which is statewide. So we have rebates for the rooftop units themselves. Take your existing rooftop out, put one with a higher SEER rating in it, and get X amount of dollars to help you do that. So those rebates exist. And then there's ones for bigger units. You got to do a little math on the big units. But those exist for small and big units up to any size. You got a 100-ton rooftop unit, you can still do this. The smart thermostat rebates we talked about last time on session number 2. So those are out there if you want to upgrade your thermostats there. We have the economizer that you can retrofit onto units, $200 per rooftop there. We have the demand ventilation that we had talked about. And then we have the advanced rooftop controllers that we talked about today. So lots of ways to get some free money on there. So what I'm going to do now, if everybody's cool with it, let's do these real quick and then we'll do the Q&A stuff. That way people, if they need to check out, they can. So once again, thanks for our sponsor, WPPI. They sponsored all 3 sessions, which is awesome. And a lot of the people on the webinar are their customers, which is great. And this survey will pop up when you exit, go to webinar, it'll pop up for you. Please fill it out. Just fill it out with all 5s because I'm so awesome and I know no negative feedback. So give me all great stuff. No, I'm just kidding. Give me honest feedback. That's totally cool. No problem there. I won't be mad at you. And then we do have some other webinars coming up at Slipstream. If you're interested, there is a lighting webinar coming up, a ventilation webinar, and a building control webinar. The ventilation and building control ones are part of a series. So there's a part 1 to that. So you should watch part 1 first and then tune in on October 1st for part 2. All right, let me see if I can switch these cameras around here. Do we have any other questions that came up while we were chit-chatting?
No, we don't have any more questions, but we already are at noon, so if those who want to leave here, feel free to leave, and Ryan, I will let you to continue. Thanks.
All right. If anybody does have questions, I'm just going to do a little tiny bit of show and tell stuff, just for the heck of it. I can move around with the laptop easy enough. I look at my nose. Interesting enough. Minimize that. Can you guys hear me okay?
Yes, I can hear you.
Okay, sweet. All right, so just for argument's sake, I didn't light this unit up very well yet, but the other ones I did. I'm only going to show you this one briefly. Your typical rooftop unit is going to be having a belt-driven fan like this. So on the left-hand side there is the motor. This little guy. Point at the same time. This little guy here. This is my motor. This is my fan assembly. Both of them have a pulley on it, and there's a belt that connects the two. This is the most common scenario. There's lots of things to be discussed on here. For one, there's shipping bolts that come in here. Mine are removed because I don't need the shipping bolts right now, so I'm running the unit. The shipping bolts are there to keep this thing from shaking while we're trucking it around the country. Once it's on the rooftop, I want it to be able to shake. Not the whole unit, just this sled that the fan is sitting on. So this fan is sitting on 4, in this case, rubber isolators. A bigger unit would be sitting on 4 springs, and I want to take those shipping bolts out so that way it can move up and down, and those isolators will absorb it. So if you have noise problems, that's one of the very common things you go look at and like, oh, whoever installed this 4 years ago never took my shipping bolt out. Dang it. So that's something to point out. The other thing to point out is these belts need to be lined up very evenly, and we have a whole process to do that. If you need help, we've got a video showing people how to do that specifically. But if the belts are on a slight angle, they'll wear funny, which means your belts will break earlier than normal. This belt should be lasting at least 6 months till the next season. If you have belts breaking 1 or 2 months into it, that's not right. So you make sure the belts are lined up to avoid that. And then you can move things around. Like these guys can slide back and forth to get the right tension on the belt, and they can slide in and out to get things lined up properly. We can also change out these pulleys or sheaves to get you a different amount of airflow. That's kind of the old school way of doing it, right? The newer way to do it would be to have a VFD on here, and then we change the VFD to get different airflow instead of changing out the pulleys. Even newer way to do that would be a different type of fan. So you're going to start seeing fans like this. I don't know how well you guys can see that right now. This is a vane axial fan. Inside there's a variable speed ECM motor. Although in this particular case, I'm not varying it. The controller in the unit is actually just running it in a 2-speed fan for the reasons that I said before. The economizer controller can only handle 2 speeds right now. So he's running it in a 2-speed fashion. And I'm getting that accomplished without the VFD. So there's no VFD on this one, but it's doing the same kind of thing. You can also have ECM inverter-driven motors that are not a vane axial fan. They're more of a traditional fan. But this is kind of the way we've been doing it for the past 15, 18 months. At least at my office, we standardize on this. We don't do it any other way. Behind here, you'll see that we have a cooling coil. In this particular case, I have 2 cooling coils, and I know you can't see that very good here, but there's one here and one behind it. The one behind it is the regular cooling coil. This one is that humidizer coil that we were talking about, and that's why we have these extra valves on here for that sequence. So normally you wouldn't see that. The valves wouldn't be there. This coil wouldn't be here, and we'd see another coil just another 6 inches further back on this guy. If you have an economizer, there should be a sensor somewhere in here for reading the mixed air temperature. It might be, in this case, we put them on the bottom of the cabinet. If you had the other blower that I showed you before, sometimes they screw it right to the side of the blower, hopefully with little short screws, because big screws would not be good. I'm going to skip all of the control widgets and stuff like that over here because we talked about that on session 1. I did want to give you a different angle view of the heat exchanger because before we looked at it only from the combustion side, but I got the panel off of this one. We're in the lab today, so I can do whatever I want basically, versus last time we were on a real live unit, which makes it a little bit harder. Here you can see the heat exchanger. In this case, I have 5 tubes on here. Bigger units will have more tubes. Smaller units will have less tubes. But the combustion products, right? So I had this burner
that was lighting off, blowing flames. Blowing flames sounds weird, but blowing flames into the heat exchanger. And then what happens is all that heat, everybody gets nauseated by my moving around. All that heat runs through these tubes and comes back to their side and exhausts out over there. But the air from the system, this fan right here, that pulled air to the cooling coil, he's then taking that air and injecting it down into the heating system. Now, we wouldn't run the cooling and heating at the same time. It'd be one or the other. But the airflow is always going to go to the cooling coil, down through the fan, and into the heat exchanger. And then from the heat exchanger, it's going to go down into space. Now, there wouldn't be wood here. That's just for shipping purposes and to keep it up on my rack. And instead of you seeing my floor down there, it would actually go down to the ductwork connection. Here's a view of the economizer. This is a modern economizer. If you remember from session 2, we said if the gears are on the outside, that's a pretty good indication that's a low leak economizer. And you probably can't see it, but there's also seals on the edge of these dampers. So in this case, we got a hood on here. Oops, I just hit one of the panels. We got a hood on here. There's different ways of looking at that. Oh, except for what did I just click? Oh, there we go. There's a hood on here. He's going to suck outside air in for both fresh air and for free cooling purposes. Down in the bottom, which we won't be able to see very often, there's going to be these little dampers that can open up to let air out. So air gets sucked in here, and we have a bird screen on here because we want birds flying in there and making nuts and weird stuff. Air gets sucked in here for fresh air and for free cooling, and any extra pressure in the building gets relieved by these little dampers. Two of them up in there. On the other side of doing that, here's that damper sucking fresh air in. It happens to be closed right now because the unit's off. So air would be sucked in there. It would go through the filter and then into my cooling coil, into my fan, into my heater. If I didn't want fresh air because it's nighttime, or I only wanted a little bit of fresh air, then he will be open partially. And then right here will be the rest of the air. So coming up the bottom of this unit will be my return air. Right? Supply air is going down the one side, return air is coming back on the other side, and that return air goes through. So this damper can either bring return air from the space, or you can shut that and open up the outside air and bring outside air from outside, or some combination of that. My actuator for the economizer. If any questions got generated from any of that, let me know. I do have another unit. I have one open and one fully closed, except I took a couple panels off this guy just so we can run it. Just because these little tiny van axial fans, I just want you to hear them because they're freaking quiet. So I'll turn one of these on. You got the panels off right now. I don't know how well you guys can hear that, but this unit's actually running right now. Now this one happens to be a single stage fan, whereas this guy over here was a 2-stage fan. This guy's a single stage fan, which means he's running at full airflow. And I'm standing right over the top of this thing having a conversation with you. I originally didn't have this in my plan to talk about that, about these units being so quiet. But I just installed one of these units last week in my own building, and in one of my classrooms, and it's so freaky quiet. Like literally, the students that came back the next week were like, "Is the air handler running?" I'm like, yeah, it's on. Why? Like normally we hear it, and it even shakes the projector screen a little bit. None of that. It's like deadly silent. It's crazy awesome. Did we generate any other questions anybody wants to ask, Ty? I'm assuming no other questions.
No, I don't see any questions.
Okay, that's fine. If anybody does have questions, you're more than welcome to send them in, whether it's regarding rooftops or economizers or heat or boilers or anything else. And if anybody wants to travel down to one of my labs and come do hands-on training, that's totally cool as well. We love that kind of stuff. All right, well, we're probably wrapped up then, is my guess. Sorry, we went 9 minutes late. That is standard Ryan. I don't think I've ever yet had a webinar end on time, so I apologize for that. Actually, I really don't. I don't know.
Thank you very much, Ryan. Really appreciate the time, and thank you to sponsor and all the attendees. Thanks.
Sweet. Thank you guys. Appreciate it. See you next time.
See you. Bye.